OpenAI has a 175 billion parameter model. You thought that was large? That's cute. Check out Google's 600 billion parameter model, 600 billion floating point numbers doing things at the same time. This has absolutely become a body part measuring competitions between companies. Google be like, oh, GPT-3, I spit on you and your little tiny 175 billion. Okay, let's stop kidding. This is a giant model that Google has trained right here. The paper we're going to look at today is called GShard, Scaling Giant Models with Conditional Computation and Automatic Sharding by Dmitry Lepikhin et al. Of Google. And this paper basically tells the story of how they built this 600 billion parameter model, how actually they attempted to build a model that had 1 trillion parameters, but just didn't manage to quite train it. And this is all using this system called GShard. So I haven't actually seen the code out for GShard yet, but I'm going to maybe assume that this is something that they're going to release at some point. Who knows? Or maybe I just haven't seen it yet. So this is basically describing a system on how to train these giant models. So if you have watched my video on GPT-3, which of course was this 175 billion parameter model of OpenAI, which already was record breaking, the paper was very much like, oh, we built a model and look at what things it can do. So that was the OpenAI paper. This paper here is like the complete opposite. It basically says, oh yeah, we do language model, but here is how we built the model, which is, equally cool. So OpenAI basically just made everything bigger, and here they say to make everything even bigger, you need some tricks in how to build models, and they've developed this entire framework to build these giant models, and this paper mainly describes that framework. And the actual task here, which is machine translation, is almost sort of a side thing in the paper. It's just a task to showcase what this system can do. So this is very much an engineering paper rather than that much than a machine learning paper, and that's how you have to look at it right here. That being said, the machine learning results are of course quite impressive. If you look at this graph, here you have a quality gain. So it's a difference in blue score, and this is a quality score for machine translation over the previous state of the art, so over their baseline, which, as you can see, here you have 37 billion weights, 150 billion weights, and 600 billion weights, which they only train. They train for, 2048 TPUs for just 4 days. They stress this is very efficient because they just have to train it for 4 days on 2000 TPUs. Absolutely crazy. So let's have a look at what this paper does. If you enjoyed this at the end, consider sharing the video out if you like it, and tell me what you think about this stuff in the comments. All right. So we'll go through the abstract, and then we'll go through highlighted sections of the paper, because the paper is 23 pages long, so I won't be able to cover everything. Just kind of give you the high-level ideas and highlight a few things. Actually, let's not go into the abstract. Let's go into, these results first. So as you can see, they managed to continue the trend. The trend in NLP has always been, and at least since transformers were invented, the bigger the better. Like larger model, larger data, more compute means better performance. And this is sort of unbroken here. As you can see, if you increase the number of parameters in these models, you do get a very, very big gain in these blur score. Though it sort of seems to be kind of a logarithmic scaling, like you have to keep doubling and doubling and doubling the number of weights, sort of like Moore's law in computation. You can see that at the same time, the training wall time is going down, and the computational cost of these models, it doesn't scale quadratically like you would expect. It scales linearly. And that's the big difference here in how these authors scaled their model rather than how the OpenAI authors scaled their model. So in a traditional traditional transformer looks like this. So it has these blocks of attention. If you don't know what this is, I have a video called Attention is All You Need. I explain how the attention blocks in transformers work. So this is nothing different. These are just transformers, standard transformers. There is an encoder and a decoder. Everything works as you know. So you have these blocks. You have n blocks. These are the number of layers that you have. And in these blocks, you always have an attention layer and then a feed-forward layer that acts on the tokens. So without repeating too much what an attention mechanism does, basically you have input tokens. So this is a sequence. It's technically a set processing unit, but we use it for sequences of text. So here you have 6 tokens, a sentence of maybe 6 words, and then you transform it with the attention layer by having this attention mechanism that routes information from from positions to other positions. Maybe like this, route this here, route this here. And then you have a feed-forward network that is applied on a per token basis. So each of these tokens now goes through this feed-forward network and is kind of transformed. So the embedding of that token is transformed by that feed-forward network. Now every token does this, and it's always the same feed-forward network. So this network here is the same as this network. Now usually when we talk about scaling transformers, we talk about this part right here. We talk about the attention mechanism, and also we talk about this part, the number of layers. So we talk about scaling the number of transformer layers, more layers, more layers, more layers. And if we want to scale the attention mechanism, what that basically means is we increase the context size of the text we can input. So transformers are very limited by the size of this context right here that they can take. The original transformers started with something like 512 tokens that they were able to take because this attention mechanism has quadratic complexity. This went up, and the OpenAI GPT-3, I believe, had a context size of 2048 tokens, which if it scales quadratically, that's quite an achievement. And also it stacked the layers very, very deep. Now, in this paper, they scale the transformers differently. They basically leave the context size, and I believe their context size is 1024, so significantly smaller than the OpenAI context size. And they don't scale the layers. So their largest transformer is 36 layers, whereas I believe GPT-3 was, maybe correct me, but I think it was like 90 or 100 layers or something like this, at least significantly larger than this. Instead, what they scale is this part right here, the feed-forward layers. Now that might seem counterintuitive, but they basically say, what if we didn't only have one feed-forward network right here, but we had many? Right? We don't always have the same. We have many feed-forward networks, different ones, that can do different things. So that's what they call experts. Each one of these feed-forward layers is an expert. And then you have yet another routing mechanism, kind of like in attention. You have a routing mechanism that decides which tokens go where. Okay, so this token here, this token here, this token here. And the implication being that different tokens, different parts of the input you want to transform require a different kind of transformations here. And these different experts can sort of specialize in how they transform the input. Now their task here is going to be machine translation as a multitask setup. So what you'll have is you'll have all kinds of languages like French and German, and maybe like a lot of languages. I don't know any other languages. And you want to translate all of them to English, and you want to do it using the same model, right? So these experts here, they might specialize in, the individual languages. Like maybe you will have to handle a pronoun differently if it comes from German than if it comes from French. You want to do it with the same model at the same time. That means you maybe want to have the one expert specialize in German pronouns and one expert specialize in French pronouns. Also, you can think of the experts as maybe one specializes in question words. It doesn't matter which language they're from, and the other one specializes in some sort of other kind of linguistic feature. In any case, this number of experts here is, if you want to scale that up, then that becomes the bottleneck of the transformer. They go up to 2048 experts in parallel. So that doesn't fit into a single accelerator anymore. And that's why the entire system has to be sharded. And that's what they call GShard. So GShard, the main application here is going to be how can we build this giant model on many distributed computers where the attention mechanism isn't the problem. The attention mechanism we just distribute like we do data parallelism. The attention, it lives on all of the accelerators, it synchronizes and so on. But the experts here, there's only, so this expert lives on machine A, this expert lives on machine B, this expert lives on machine C, and then we do a hard routing. So we don't do a soft routing like in attention, we do a hard routing where one token goes to one or at maximum two experts. So this is sent to these machines, and then after the machines, you kind of gather all the results back right here. So GShard is the system that enables this sharding of these experts and everything in between, everything that is necessary. But it can also be applied to shard any computation, and that's why it's so cool. So here you see what they do. They take these transformers, and they always consider a block of two transformer layers. So this is a block of two transformer layers. You can see there is twice the attention, and there's twice this feed forward. So in one point, this feed forward is just a regular, everything, all the tokens go through the same network. So that's like a classic transformer. But here, you have a lot of these different experts, and the tokens are routed to these experts. It's important that the tokens are hard routed, right? If the tokens were soft routed, you don't gain anything because every token has to go through every expert. But here the tokens are hard routed to the expert, which means that you can, if I have an input size of 1024 tokens, maybe only 10 go to this one, and maybe only 10 of those go to this one. Now you also have a batch size, of course. I haven't actually looked at what the batch size here is, but you usually have quite a large batch size in these things, like maybe a batch size of 1,000 as well. So ultimately, what you'll end up is, 1,000 times 10 tokens going to the first expert and so on. But still, you can significantly parallelize this computation. Okay? So this, if you use GShard, this is going to result in the following in the thing on the right, where you have two machines. This is machine 1 and this is machine 2. You can see that the machines will, what happened here? Oh, someone made a PowerPoint mistake. So you can see that the attention, everything is shared between the machines. So this here and this here, these are synchronized. The weights are synchronized, right? You simply do a data sharing. But here, you can see that you have model parallelism. Model parallel mixture of experts, where on the first machine, you have the first expert, and then you have E devices, and on the last one, you have the last expert. And then it's all routed out and routed in again, and then you can continue your transformer. And this is layer after layer. So what's the problem here? The problem is that an operation like this is going to incur significant sort of overhead in terms of communication and so on if you were to do it naively. And it's going to be a real pain to program this. And that's why GShard is made to do all of this automatically, and you don't incur much of a cost because you distribute. So what's the difference to the old scaling? Why don't they just make transformers larger in number of layers? And that's because this is, I guess, what OpenAI ran into as well. If you make transformers simply larger in number of layers, if you make transformers larger in the attention mechanism, it just won't fit into memory at some point, and you'll have to shard that somehow. And you can do this with GShard. If you scale it in number of layers, that incurs significant cost where you have to wait, because you have to forward propagate and then you have to backward propagate in your training sequence. And if you have just too many layers, then a lot of the frameworks get at their limit, where at some point they say, well, I still have to wait for the signal to come back in order to continue. And they explore this in this benchmark right here. You can see they say the largest model, the 600 billion parameter model that achieved the best translation quality, was trained with 2000 TPU v3 cores for 3 days, a total cost of 22 TPU core years. In contrast, training all 100 bilingual baseline models would have required 29 core years. So the model here is faster than if you train them individually, but if you want to train a single transformer that is just very deep and achieves reasonable performance, you have to invest a lot more. Our best quality dense single transformer model, 2.3 billion parameters, so it's also significantly smaller. Achieving this was trained with gpipe, which is a previous framework. So gpipe is kind of a task runner that also distributes computation. Was trained with gpipe on 2048 TPU cores for 6 weeks, or a total of 235 TPU core years. By the way, for if you have $1 per TPU hour, that'll only I guess set you back about 2 million or so, easy peasy, or even 200,000. Just, you know, a tiny bit of money. But you can see that this transformer model that is dense, which means that is a classic transformer where you stack the transformer layers, you stack them, you stack them, you stack them. In fact, it has 96 layers, their baseline. 96 layer transformer model. That's sort of what OpenAI did. They just kept stacking the transformer layers. You get a model that has less parameters and trains for much longer, and its performance is only about this good. Whereas here, if you scale not into depth, but into width of these experts, and it's not dense, but it's sharded, which means it calculates this in a kind of sparsified way because it has this hard routing, you can scale up to a lot more parameters. So 600 billion parameters, over 200 times more parameters than the deep model, and you can get a much better performance. Okay, so this is what is different here. It scales into these experts rather than scaling into depth or size of the attention mechanism itself. All right, the question, I guess, that you come up with if you're a machine learner is how do you backpropagate? If here you route to these different experts and you do a hard routing like here, how do you backpropagate the signal? Because it seems like you need a soft routing, but this has been handled. In fact, this mixture of experts has been introduced previously in a paper, I think, called Outrageously Large Language Models or something like this. So they've introduced that, you know, it still works. So backprop still works through. So basically you have a backprop path through here. And because you put a little bit of noise in this routing, every path gets explored a few times, and therefore you have enough backprop signal to make it work. It could technically fail, but they do observe generally that it does work if you do this kind of hard routing with a bit of noise. All right, so where do we go from here? As I said, this is an engineering paper, and it's a long engineering paper. So they set up their they set up a lot of the details of engineering directly in the paper, which we're not used to in the machine learning world. They really detail how they shard things and so on, which is pretty cool. But I invite you to look at the paper yourself if you really want to know what's going on right here. Suffice to say, as you can see right here, what they do is, this is the input right here. And then they have this weight matrix, which is this is learned routing weights, okay? So you have trainable weights that decide how to route the input, and that's dependent on the input. So you have a bunch of inputs that comes from the lower layer, and this matrix right here determines where to route them. Basically says, okay, the input is a vector like this. I know that must probably go to the expert number 3. Okay, and you have a softmax across that. So it's a soft assignment to the experts. So once you've done the soft assignment to the expert, you do a hard assignment by collecting the top 2. For each token, you collect the top 2 experts, and you only send it to the top 2 experts, and you ignore all else, which is not a lot, right? At times there are 2,000 experts in this system. And yeah, you distribute and you have some noise. So with a random probability, you actually don't even send it to the second expert. You just leave it at the first one. And with some noise, you send it also to the second one. And I think that noise is part of what makes the system work a bit. And then you also have this auxiliary loss right here that you add on top, which just makes sure that you distribute evenly. So this encourages the system to distribute the tokens evenly, because, what it penalizes is this here is the mean assignment to each expert. So it penalizes whenever the mean assignment is out of line, basically. So a distribution assignment to the expert where one expert gets a lot of tokens because, I don't know, it happens to be really good at something, so all the tokens are routed to it, and the other expert don't get a lot. That's penalized. So you encourage the system to distribute tokens evenly between those experts. And then there are also like upper limits where you drop tokens and so on. They really build a system that is out for performance rather than machine learning correctness. So they demonstrate how to do this in sort of code with their system. And the cool thing about their system is that you don't have to do much. What you'll have to do is just specify which tensors are sharded along which dimensions, and the system does the rest. So this is pretty cool. So this here is this mixture of experts as you would write it in code. And they make use a lot of this Einstein sum notation. If you don't know what the Einstein sum notation is, it's a general notation to describe matrix or tensor multiplications. So for example, if you were to multiply 2 matrices, you could have a string there. You describe it as a string, and it comes from how Einstein wrote up the kind of tensor contractions in his work. So if you want to multiply 2 matrices, you could put the string A, B, B, C goes to A, C. So this, and then you put 2 matrices right here. This would tell it, okay, I have one matrix, I'm going to call the axis A and B. I have another matrix or tensor where I'm going to call the axis B and C. Now I have the resulting tensor, and I want the first axis to be A, and the A is this one. And I want the last axis to be C, and the C is this one. And B is nowhere, B is not in the output, which means it should contract over B. So it should sum along B, it should multiply along B and then add. So it should contract over B. So this here describes a regular matrix-matrix multiplication. Now, if I could do something else, I could do something like just a element-wise product. An element-wise product would be something like this. AB, comma, AB goes to AB, which means here I have A in the first input, and here I have A again. And so you already see that you can, even though these are different tensors, you can call the axis the same, which means that they're going to somehow be multiplied together. Now, if you leave it away here, it means that it's going to be contracted and therefore the axis no longer exists. But here we don't leave it away, which simply means that these axes are going to be multiplied together. And the same for B right here. So this describes an element-wise product. You can go really funky with this. So this here would be a row-wise dot product, where A is for all the A's, it's element-wise, but then over B, it's contracted. So, you know, you can go wild with the Einstein sum notation. You can describe a lot of things with it. So here is this algorithm to distribute the computation among these different experts. So you have the inputs and the weight matrix for they call this the gates function. That's the routing function to these experts. So what do? First of all, we have these tensors. They have this grouping dimension right here. So they come along groups, which in our case we could maybe say these are batches, or the batch dimension. So they come across groups, and there is the sequence length, and there is this M right here. That's going to be the feature dimension, the M. And you can see the M is contracted. So the M is no longer here. So the gating function is going to route each input token right here to one of the experts for each thing in the group. So you can see you can express this with an Einstein sum notation. Then you have a top 2 gating, which selects the top 2 from each of the from each of the entries. And that gives you this dispatch mask and the weights that you have to use at the end to combine. You can use the dispatch mask in order to distribute the inputs. So you have reshaped inputs and so on. So I'm not going to go through all of this right here, but you can express all of this in terms of the Einstein sum notation. And you can express pretty much any sort of computation that is along the line. You can express the attention mechanism and so on. You can express the feed-forward layers in terms of these Einstein sum notations. And the underlined dimensions here are the dimensions where we want to shard the computation. So here, because we have this G underlined, that means that we are interested in sharding the computation along this axis. So this, as I said, this is the batch dimension. This is your classic data parallelism, which means that the first machine gets the first couple of data points, the second machine gets the second couple of data points, and so on. And you can see in the weight matrix, there is no sharding, which means that the weight matrix lives on every machine as a copy of one another. This is different from here, where you can see that what we're now going to do is, here it's still sharded according to the batch, but we now are going to shard this according to the different experts. So we're going to route whatever the inputs are to these experts. And then we're going to execute the computations on the experts. So this is now sharded according to the experts. And at the end, right here, you can see this is still sharded according to the experts. We're going to put it back together, and now it's sharded according to the groups again. That's what we said. We have the input right here, the inputs, and the inputs are maybe distributed according to machines, right? We have these go through the first machine, these the second, these the third, and so on. This is your classic data parallelism. But then we have all of these experts. And now all of a sudden, we're going to route these things to the individual experts. And we're going to execute the computation in parallel on the experts. And then after that, we're going to put back together from wherever we got them now F2. So this goes here again. And so this is just the reverse of what we did before. So right, like that. So you get all of the outputs again. I hope you kind of can imagine how this happens. So the first difference is that's sharded according to a different dimension. And the second difference is that when we shard in data parallelism, we execute the same computation on all the machines, which means that we have the same weight matrix. If we do X times W in a feed-forward layer, and we shard this thing here in data parallelism, what we do is we send the X to different machines. We split the X, we send it to different machines. This is X1, X2, X3, X4. But we always multiply it with the same weight matrix. That weight matrix lives on all of the machines and is regularly synchronized. It's kept synchronous in some way. Whereas if we shard X to the experts, then the experts have individual functions. So the expert 1 is different from the expert 2, is different from the expert 3, and so on. Which means that before it wasn't important where X was routed, because we would execute the same computation. So we can just, shard it according to, the first 10 go there, the next 10 go there. But here it's now crucially important where they are routed to which expert. And that's why we learn the function that is going to route them. So this is learned. This is this first line here. These are the weights that we learn to route. Then we route right here. And we calculate we calculate the feed-forward layers on the expert. You see that this WI and WO, they are the weight matrices of the feed-forward layer. The feed-forward layers are, you have your input, you multiply it by WI, you have a ReLU, and then you multiply it by WO. So it's kind of a two-layer feed-forward network. So this two-layer feed-forward network, as you can see, this is sharded according to the experts. And then, and the important part is, of course, that here, the weight is also sharded according to the experts. And that's what makes each expert different. And then it's combined again down here. So I hope you kind of get the idea of what this algorithm does, and the fact that we shard according to these experts is in fact different than your regular sharding where you shard the data like the batches, but keep the model in parallel, keep the model synchronized. With their system right now, this is how easy this is. So before, we simply stated our algorithm in Einstein sum notations. There's no way to underline code and that magically happens something. That was simply for us to visualize. Now we want to apply their system in order to make this actually sharded. And with the GShard system, and as I said, I don't know if the code is out or it will be out, but with the GShard system, this is basically all that you have to do. So you have these functions, they're called split and replicate. What replicate does is it takes that weight tensor and it replicates it on all the machines, and that keeps it synchronized, right? This is a computation where we simply want to shard out the different to the different machines, but keep it synchronized. And you can see if you do this, this is the operation, then the system knows this here is replicated across the machines. So that means I'm going to distribute the data points according to this G dimension, according to the batch dimension, and multiply it with this matrix according to this Einstein sum notation string on all of the machines, and I'm going to keep this tensor in sync. Okay, so the system knows. As opposed to that, you have the split tensor right here. So the split, what it does is it splits a computation, here the dispatch expert inputs, it splits it according to a axis index onto d different machines, or into d different parts. So you see here you calculate how you should do the routing, and the resulting tensor's first dimension is this E dimension. And then you say that should be split, according to this first dimension, onto d different places. And these d different places are now separate. They don't have to be kept in sync. Everyone has their own weights. And now when you do this, according to this E dimension, you can see, because we know Einstein sum notation now, you can see this E appears here, here, and here. So this operation is going to be applied element-wise. That means independent of each other in the direction of this dimension. The system understands that since this tensor is sharded according to that dimension, I have to execute this on each of these entries in separate, on each expert having their own weight matrix right here. I hope this is a bit clear, that their system makes it super easy. You can basically do two things. You can say, this thing here is my classic parallelism, where I want to keep it in sync. And this thing here is where I want to split up and do different computation on the different parts. And then they have also a general function that is more powerful. Yeah, you can auto partition and whatnot. So they have they have this. We implemented the partitioner in the XLA compiler, which means that anything that can translate to XLA is a target for this system, and that's TensorFlow and PyTorch can do this. So technically, this can come to any of those systems. But of course, who has their 2,000 TPUs lying around to make use of this? But no, I'm kidding. I mean, they here use it for transformers, but I am very excited to see what people can come up with for the system. I believe a system like this, where it's super easy to shard, and they have some, they talk about, okay, we do this single machine compiler, so the compiler is also fast and so on. I don't even want to go into this, but this is very well engineered, it seems. And they basically implement this for all of the operators. So I'm very excited to see what people can come up with outside of the traditional applications. I think there can be new types of models developed simply because we have a system like this that makes it easier. So yeah, I'm excited. So here they show a bit how this works on the example of this Einstein sum notation. So here we want to do this thing here, which, if you remember, this is the operation where we want to route the input to these experts. So we want to start with something that is sharded according to the batch dimension. That means that we have different parts of the batch on different machines. And we want to route this and finally end up with something that is sharded on the different experts. So this is what the system does, is first you have, these here are the different shards, right? You want to multiply this, as you can see, this and this right here means that this routing table is also sharded according to the same machines. So you have the 0 is all on the same machine, the 1 is all on the same machine, and so on. So what you want to do is you want to contract. You want to contract according to this S dimension, right? Which we have omitted right here. And if you multiply that, we omit the S, so this is not much of a graphic right here. But then they have this reshard operation where they do, and you don't have to worry about this. So from here to here, there is this reshard operation that just shards it according to E. Yeah. I find this to be a bit more insightful. So if you have something like this, which is a regular matrix multiplication, right? And you want to contract along B, this is exactly the example we had before. So here is a situation where our tensor is sharded according to the B dimension, and this tensor is also sharded according to the B dimension. And you want to do a matrix multiplication of the whole tensor. So what can you do? You're supposed to multiply these two matrices, but they are sharded on different machines. Now, if you consider what you actually have to do is you have to multiply each row here with each column here, and that in an element-wise fashion. So that distributes according to, you have to multiply this by this, plus this by this, plus this by this, plus the red by the red. So you can simply multiply the 0 tensors together, the 1 tensors together, the 2 tensors together, and the 3 tensors together. Each one will give you a full matrix, and then you can simply add all of them in order to get your full result. This is illustrated down here. So what machine 1 does, it simply multiplies its shard by its own shard of the second matrix, which will give it this thing here. And by the nature of how matrix multiplication is constructed, you can simply do an all reduce, which means you sum across all of the machines, and that will give you the full result. So this is an example of how this works. This is, pretty simple, and I believe you may have seen something like this already when you were looking at just parallelizing matrix multiplication and so on. So this system handles this transparently, right? If you're sharded like this is what the system will do. However, if you are sharded differently, the system will act differently. So here is a system, you want to do the same matrix multiplication, but the first tensor happens to be sharded according to the A dimension, and the second tensor happens to be sharded according to the C dimension. And you want to end up with something that's sharded to the C dimension. Now we have an additional constraint here that here you can see we kind of assume that this full thing here fits into memory, mainly because we want to obtain the full result. You see here, A and C should not be sharded. So we assume that we can keep that in memory. But here we want the final result to be sharded according to C, which imposes the additional constraint that it might be that the full matrix never fits into memory. So how are we going to calculate all of that? We can't do the same trick anymore. Now this GShard system apparently realizes itself when something is out of memory, and it can do a smart move around being out of memory using a loop, which basically means that it will compute entry by entry or block by block. So these are the matrices we have to multiply, and you can see that if I want to multiply this by this, that's fine. I can do this on one machine, and that will give me the block up here. But if I want the block up here, I have to multiply this by this, which is across two different machines. So what this system does is it's going into a while loop because it realizes there's not enough memory, and it kind of sends around these different slices to the different parts, each time computing a little piece. So here, first we do this by this. This is fine. But then we grab ourselves from the, we grab ourselves this one here, calculate the next little piece up here, and then we grab ourselves the number 2, calculate the piece here, and then, so this is from 0, this is from 2, the 1 we already had, and then we grab ourselves piece 3 and multiply that until here, until we have this final slice that we want. Okay, so this goes in a while loop in multiple rounds. The system knows itself when it has to do this and when it can calculate the full thing at once because it fits in memory. It's even smarter than that in that it can do these halo exchanges. So if you have to do something like this, a convolution. Now in a convolution, what you'll do if you think of an image and you want to do a convolution on it, but the image happens to be sharded. Let's say the image is so large it's sharded across 9 different machines like this. Now if you want to do a convolution, that's pretty cool, you know, here, 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 but here all of a sudden your convolution is across 2 different machines. So this system, GShard, will adapt automatically and do these halo exchanges where it kind of sends around from this machine, it'll send something to this machine such that it can do the convolution in that step and vice versa. And then this can be padded accordingly, as you can see. I think this was like super ugly to implement. If you just imagine that for each of these operations you have to think about, okay, how can I express this with these MPI primitives like dynamic slice and collective permute and so on. It's just an absolute nightmare, and I'm very happy that other people have done this, and I will probably just get to use it. So there is a lot more to this system than I've just explained. I just try to give you a flavor of what building a system like this means and how easy it is to use it. Like this, in order to implement all of this mixture of experts things, you simply go from this, which is a single machine implementation, how you would write it, to this, which is now the same, it's almost the same code, but this now you can run on however many machines. And if you compile it with the system, it will do what you expect it to do in this sharded way. Completely crazy. Okay, so they apply this to massively multilingual, massive machine translation. So 2 things, it's massively multilingual and it's massive machine, which means, I guess, a lot of machines. And the reason here is twofold. So what they say is, we have massively multilingual translation. Why don't they just look at, you know, single machine translation? And it has a very specific reason. Namely, if you have massively multilingual translation, which means that you have a lot of different languages and you all have to translate them ideally to all the other languages, or, you know, every language pair. But in this case, they only look at all the languages to English. I don't exactly know why, but I guess there must be some kind of reason. If you do this, then you can make use of a thing where there are languages that you just don't have much data on, like I don't know, Basque or something like this. There's just not that many people speaking Basque or Swiss German. There's not even a written form, a standard written form of Swiss German. So you just don't have as many resources. And for other languages, you have giant amounts of resources. And what you can make use of is this phenomenon called positive language transfer, where it happens that, for example, Swiss German is very close to German. Now, they can't understand us, which is a giant advantage for us, but still it shares a lot of similarities with German. So if you learn a lot about German, you can sort of transfer learn to Swiss German pretty easily. So if you have a system that does German and Swiss German at the same time, you can perform better on both languages because the Swiss German part of your model, the part of your model that does Swiss German, profits from the German inputs as well. Now, don't understand me wrong, there is not an individual part of your model that for each language. It's all done at the same time. But still, you can imagine that, some of these things will specialize in some of the languages. But the hope is that if you have German and Swiss German in the same training set, that if the model realizes what a question construct is in German, it will be able to apply that also to Swiss German with some minor modification. So there is a benefit of having these many languages, especially for the low resource languages. Okay, so as the number of language pairs to be modeled within a single translation model increases, positive language transfer starts to deliver large gains for low resource languages. Given the number of languages considered, which I believe is 100 here, M4 has a clear advantage on improving the low resource task. On the contrary, for high resource languages, the increased number of tasks limit per task capacity within the model, resulting in lower translation quality compared to A models trained on a single language pair. This capacity bottleneck for high resource languages can be relaxed by increasing the model size to massive scale in order to satisfy the need for additional capacity. So basically they're saying if we train all of these languages together, that will help a lot for these low resource languages, but it might hurt the high resource languages because now we would have enough data technically to train a French to English model on this giant model. We could train that. And now that we have all these other languages in there, it just hurts us because we don't have enough parameters. And we can solve this, of course, by simply adding more parameters. So that's the solution. Add more parameters and you increase the capacity of the model and you still get the benefits of the positive language transfer. So their investigations is going to be into how much can we scale this, and is there like a sweet spot because if you increase the parameters too much, you counteract this positive language transfer again. So since Swiss German and German can sort of benefit from each other, however, if we have too many parameters, and then we end up having all of these experts right here, and the tokens are always routed to these experts, and it always happens that all the Swiss German tokens are always routed to this expert, and all the German tokens are always routed to that expert. There will be no sharing of weights. There will be this positive language transfer will not happen because we have too much capacity. So the goal is to find a sweet spot between positive language transfer and this capacity bottleneck. They do use an in-house data set, which we don't have access to, but they say the training corpus mined from the web contains parallel documents for 100 languages to and from English, adding up to a total of 25 billion training examples. However, they only use from 100 languages to English. This results in approximately 13 billion training examples to be used for model training. So that's a lot. It's a lot of data, especially for translations. It's kind of a noisy translation because it's mined from the web, but still, it's a lot of data. They have baselines. So the baselines are, first of all, in order to form our baselines, we trained separate bilingual neural machine translation models for each language pair. So that means a single model for each language to English, tuned depending on the available training data per language. And then they also have a baseline where they try OpenAI style to build as deep as single transformer as possible. And by that, they mean we also include a variant of a dense 96-layer transformer encoder-decoder network trained with gpipe, pipeline parallelism on the same dataset as another baseline. So the difference again here is that this 96 layer is a dense transformer, which means that all of the tokens go through the same computation, and we don't shard the computation out to these experts, right? We do shard according to the batch, but all of them go through the same parameters. And that means we can only scale up the number of layers, and that severely limits the computational efficiency. Even if we have, your pipeline parallelism and so on, that hurts. They say training to convergence took over 6 weeks on 2000 TPU cores. That's crazy. But I guess, yeah, I was saying earlier that I always thought we were happy. I always thought we were happy in machine learning because kind of the hip science fields being biology, like genetics and machine learning, I was thought like, oh, but these biology people, they always need like $1 million grants from government to run their experiments, and we can just sit down with a laptop. This time is over. If you start a PhD now, start applying for money to get TPUs. Yeah. Okay. In any case, here you can see what this does. So they compare a bunch of models right here. So this is this big dense transformer that's going to be one of our baselines, and the other baseline here is going to be the 0 axis. The 0 axis means this is the single model for that language pair. So for each language, they trained one model only on data from that language. And that's going to be the worst thing here, because this multi-language translation in one model will generally help you if you have enough parameters. You can see all the models here have enough parameters such that the difference here, that this is difference in blue, is positive, including this baseline model right here. So the baseline model, as you can see, has 2.3 billion parameters, even though it takes that much longer to train. And that's, as we said, a function of the fact that it's dense and deep. So that hurts in training efficiency. And then you have this mixture of expert models. They always consider two things. They consider different numbers of experts. You can see it goes from 128 to 2048 experts. And they consider a different number of layers, from 12 layers to 36 layers. 36 layers still being way smaller than the 96 layer transformer here. And that's the reason why it trains faster. So it doesn't train faster. So the reason it trains faster is because it has less layers. And then the reason it has more parameters is because it has a lot of these experts. And the art here is to constrain how much these more experts hurt you. So, you could run into the same problem where if you scale up the experts, in fact, you do, it doesn't fit into memory anymore, and it's going to hurt you a lot in training efficiency, kind of like if you increase the number of layers. But the GShard system prevents that. It lets you up the number of experts without incurring the cost. That being said, it does not let you up the number of layers. You're going to incur the same cost if you up the number of layers as you have with the dense transformers. So does this help? It helps a lot. As you can see right here, there's a general trend upwards. And what's the x-axis? The x-axis is low resource languages. So you can see that as we go to lower and lower resource languages, this multitask training, this multilingual translation, improves significantly over the baseline where we only train a system for that language specifically. And these 10K examples, it's quite a bit, but it's not that much, especially since it's noisy data. So this is specifically good for low resource languages, but you can see also the high resource languages here benefit from the multilingual translation. And that's a function of the fact that we have, large enough models. In fact, you can see the larger the models, the more the difference in blue is, and there's not really an end in sight. And they also say that they haven't seen convergence in training, so you can technically train this, forever. Yeah, you can also see that the lowest mixture of experts right here is almost on par with their big dense transformer that took so much longer to train, right? So this lowest model right here, I believe it took, I don't want to go back, but it took hours or so, or a few hours to train, whereas this 96 layer dense transformer took these 6 weeks to train. Though, has to be said, the number of TPUs is not to be neglected, but if you're Google, you just have them laying around. What's also interesting here, and you can start seeing this, two things. First of all, you can see that the difference between the dense transformer and this baseline model is very low for high resource languages, but gets larger for low resource languages. This is an indication that the dense transformer, it does more to share parameters between the languages, because it shares parameters between all the things, because all the tokens go through the same computation. So it is going to be a bit better in low resource languages, but still the general trend upwards holds even for the mixture of experts. The second thing is that you see there's a crossover here in these biggest models. And what are the big models? The blue one is the one with 2048 experts, and the green one is the one with 500 experts. They're both as deep models, but all of a sudden, over here for the high resource languages, it's still true that if you up the number of parameters, you get a benefit. So up the number of experts as well, you get a benefit. But over here for the low resource languages, you see it actually hurts you to up the number of experts. And that's the phenomenon exactly we talked about before. If you have too many of these experts and you do a hard routing, that means all the tokens go a different way. And that means you don't get any sharing benefit from the multilingual translation. And they investigate a lot, and they basically claim that their sweet spot of expert in their particular task appears to be somewhere in between these 2000 and this 500 expert number, where you can see it doesn't always help you to scale up the model. Though I have to say, maybe the transformers, maybe they need a ResNet moment. So I believe in computer vision, it was sort of the same problem that we tried to build deeper models, and why, like, okay, this is more width, but yeah, I think there might be some breakthrough on the horizon where someone just figures out how to train these giant models, even more giant transformer models with deeper layers, and then there's a new era of transformers. However, this is not that effect. I'm sorry, I said this at the wrong place. This is not that effect. This is to show that in this case, we do benefit for the high resource languages because we increase capacity, but for the low resource languages, we suffer if we up the number of experts too much, because they don't share any parameters anymore between the languages or between the different parts. Like, it's not a necessity that the different languages are going to be routed to different experts, but it's probably going to happen, right? There's no hard-coded thing that says if it's this language, it needs to go there. It just probably is going to happen this way because the different languages are going to be needed to be treated differently, and therefore the system learns to route first and foremost those two different experts. Here you can see the model sizes, including this 60-layer model with 2,000 experts that they didn't manage to train. They said they had numerical instability, but that had 1 trillion parameters. And I'm pretty sure they must be quite mad about this, right? Like, you have the trillion parameters, even though it's not that much bigger than the 600 billion. The trillion, it would be cool to write a paper like a trillion parameter model. But for now, they are at the 600 billion mark, and they simply want to tell you that they have actually compiled a model that's that big, just didn't manage to train it. And yeah, that's here is where I wanted to say that maybe we're waiting for the ResNet moment, where all of a sudden someone figures something out that makes the training of basically infinitely deep transformers possible. Like we made the training for almost infinitely deep CNNs possible with ResNet. Okay, so they conclude this, and that's the investigation of what the number of experts and so on gives you. And here is a bit of a different investigation where they more care about training efficiency. So they ask themselves, how many billion tokens of input do we need to reach a given cross entropy? So here, the more tokens you need, the lower your efficiency is, right? You can see that the general trend is the following. If you up the number of layers, you get more efficient. You can see, and just look at this column for now, this 0.7 column. You can see it already pretty clearly. So here you go from 12 layers to 36. You gain efficiency. Here you gain, here you gain. Pretty predictable. If you up the number of layers, you need to see fewer tokens to get to the same cross entropy. And in fact, you can get to a lower cross entropy altogether at the end. We've known this for language models already. The other effect is, of course, what happens if we go not deeper, but wider. If we increase these number of experts, if we increase this sparse computation. So here you can see, let's just look at the 12 layers for now. Let's look at all the rows where there's 12 layers. So here you get a significant advantage by upping the number of experts from 100 to 500. But then you hurt upping the number of experts to 2,000, right? So that's sort of, you're hurting efficiency by upping the number of experts too much. And the same if we look at the 36 layer. So you gain massive efficiency by upping the number of experts, but you lose that part of that efficiency again by increasing it even more. Now we saw that this model is still the best model, but it's not as efficient as that model. And that gives you another indication that there is sort of a sweet spot between these two things, between the positive transfer and the bottleneck capacity that appears to be somewhere in between right here. So that's pretty interesting. Because we know about depth, that you can basically up and up and up and get more efficient, but width, not that much. Yeah, the largest model can be trained in under 4 days to achieving the best quality. Yes, 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 but this is just yeah. So here, oh, you can see the batch size in tokens is quite a bit. So yeah, if you have a context window of 1,000, that means the batch size here was about 4,000. So as expected. Yeah, this is just easy peasy 22 TPU core years. I've seen someone on Twitter saying this. This is the new measure for computation. No, it's no longer like flops. It's TPU core years. Just mad. And yeah. So 42 days to train this thing right here. Crazy. All right. They also have a number of investigations in other parts of efficiency, like per device memory consumption. You can see here that as you up the number of experts, you can see here, your weights don't go up, because as you up the number of experts, you can just up the number of machines, and the per machine weight usage will be the same, right? Because the experts are independent of each other. Each one has their own weight matrix. So you can just add machines and you keep your weight requirements the same. However, if you go deeper, then your weights increase because you're now deeper. You have more layers. You have so also your transformer weights will be higher and so on. So you go deeper right here. You see 36, 60 layers. Your memory consumption increases for the weight. And also, this is the other big part in transformers, right? The activations that you have to save. Because as we said, if you have a transformer and I have layer, 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 I basically have to keep around each of these signals in order to do back propagation. And that's why also the activation here increases as I go deeper. Now you can see percentually it decreases again here. So what's happening? Technically, you don't have to keep these things around. You can also, once the signal comes back, you can recompute them from the beginning or from an intermediate point. Now, this increases computation, but saves the need to store the activations. And apparently, GShard, yet another thing it does, is it will recompute as necessary the activations if it realizes that you don't have enough memory to store them. So all of this is pretty crazy, honestly. And they look at where the different computations go. And I don't want to go into this. And they have these micro benchmarks where they really show that the increase in complexity is really according to square root of n, because that's how long it takes to distribute along these along these experts. There's a lot to this paper, and there's no time to go through all of it. I think this video is already way too long. I hope I have given you an impression of what's possible with this system. And as I said, I'm excited what people can come up with. Just to say that in the appendix here, they detail that they have done this for all the operations in XLA. So for example, convolution. This is so ugly how you have to implement the convolution, because you have to padding must be correct across these across the sharded machines. So there are no experts anymore. This is just GShard. The padding has to be correct. The strides have to be correct. Data needs to be exchanged according to the machines. The window size needs to be correct. Blah, blah, blah. It's thank you for doing this and not having to do it myself. Yeah, I'm excited. As soon as the code's out, if I get hold of it, I'll link it, or you'll find it once it's out. If it's already out, I'm just too dumb to see it. I enjoyed reading this. It's different than a machine learning paper. It kind of shows you what goes into engineering a system like this and how easy it can be, if it's engineered well, to then apply it. I think this is going to be extremely helpful to the community. And with that said, 23 pages later, see you next time. Bye-bye.